If you treat this with aqueous acid and heat, what does acid do to an ester? Hydrolyzes it to the carboxylic acid. And so we get ester hydrolysis. The name for this type of compound, carboxylic acid with a ketone, not alpha, but beta. So what do we call it? Beta keto acid. Beta keto acids are prone to decarboxylating. We'll lose CO2. Here's the CO2 right here. Carbon with 2 oxygens. The H will end up here. When the H ends up there, what do we get? We get that molecule there. Okay, how does decarboxylation happen? We're under acidic conditions, so we're not going to deprotonate anything. Now your book probably shows a transition state here. I'll let you look in the book and learn about the transition state. I'm going to show you like this. Because anytime you make a pi bond and kick off a leaving group, that's easy to do, using a lone pair. Let's make a pi bond here, kick this off. What does that give? Now this is not the exact mechanism, but this can be some of the thought process. That's going to be a minus, and what are we going to get over here? COOH. It's going to be a plus charge. Make this pi bond kick off the leaving group. Whenever I first told you this, that we could do this, I said, if you've ever seen it be a minus, it can serve as a leaving group in this, anytime you make a pi bond kick off a leaving group thing. Have you ever seen that be a minus? Yeah, that's an enolate. So that means in my description of this, we can do this. Now how do we get this plus CO2? Well, this just needs to take the H, and you get that proton transfer. Okay? Basically, whenever you decarboxylate, the enolate is just serving as a leaving group. Or enol. Now again, this is under basic conditions, acidic conditions. Under basic conditions, it'd be easier to show, because under basic conditions, well, it's just as easy to show, but it's more correct. Whatever's here. Because under basic conditions, you can have an anion, and that's a stronger sort of push off. You can kick that off. You make CO2 plus this anion, and then it can pick up a proton. But basically, whenever you decarboxylate these, the enol or enolate, enol or enolate is serving as a leaving group. Essentially, that's what's happening. You can look in your book for a more discussion of this. There's actually a transition state you could show where this H is actually taken by that oxygen. And what you get first is an enol with the H on the oxygen, but then the enol tautomerizes to the ketone. You can look in your book. The take-home message here, carboxyl groups that have a carbonyl beta to them are very prone to being lost to CO2. Carboxyl groups that what? Have a carbonyl beta. Does this carboxyl group have a carbonyl beta? Yeah. So show the product of this. What drives this reaction? This molecule, especially if heated, especially if you heat this, it will give you that plus CO2. What drives this? Entropy. One molecule going to two. Yes. Typically a little bit of heat, you'll decarboxylate these. What if you take this molecule here and heat it? What are you going to get? I see a carboxylic acid. I see a couple of them. let's see, if you heat carboxylic acids, you can lose CO2. Where, when, how? Carboxyl group that has a carbonyl beta. Does one of these have a carbonyl beta? There's one. That's alpha beta. Oh, there you go, right there. Here's one, alpha beta. Ain't no carbonyl beta in that one. That one ain't going to eliminate. Because if you try to eliminate this, you'd have to kick off a carbanion that's not stabilized. That won't do. But here we can kick off a carbanion that's stabilized, essentially. What do we get? We lose CO2, and we get hopefully I drew that in the same number of carbons. We lose CO2, this H ends up here, essentially. Carboxyl groups that have carbonyls beta. Beta keto acids, but there's other types of carboxyl groups that have carbonyls beta. That's a beta keto acid right there. Boom. Heat it up, lose CO2. It's probably a solid. Guarantee if you take a melting point of this compound, it's in the tube, you're looking at it. As soon as it melts, it'll start bubbling. What are the bubbles? CO2 coming out. In biochem, you'll see acetoacetic acid. It's a lot. Ketoacidosis. Okay, let's look at a variation of this, or malonic ester synthesis. Here we start with a diester. Diester. Treat it with base. What's the base going to do? We've got two H's here. They're fairly acidic. This is a molecule sort of like this, acidic methylene. So we take the H. Get the carbanion made. And this can come in and displace the chlorine. And we get our alkylated product. I don't know if I redrew it. Who redrew it? Nobody redrew it? Good. Okay, we take this with H3O+. What are we going to do? What does aqueous acid do to an ester? It hydrolyzes it. Let's test 3. We got two esters though. It's going to hydrolyze them both. And so we end up with, we treat this with H3O+. We're going to end up with two carboxylic acids. We are also heating. Let's see, we've got a carboxylic acid here. I could point to either one. There's a carboxylic acid with a beta position, there's a carbonyl. So what is this prone to doing? That's prone to losing CO2 and the H ends up here. And when the H ends up there, what do you get? You get a product. That's going to decarboxylate with heat. I mean, you can lose either one you want, because this one also has a carbon, but you're only going to lose one. Choose a carboxyl, see that it has a carbonyl beta, that carboxyl will be lost. The carboxyl in the final product does not have a carbonyl beta, so it's not going to be lost. So here, the malonic ester synthesis actually gives carboxylic acid that's been alkylated. be good to look back at the you look back here. This was labeled as compound A. This was a indirect route to compound A. Look on the previous page, we had made compound A by a direct route. LDA just made carbanion, and then this just alkylated, and we had made that compound A by a direct alkylation of the carbanion. But this required LDA to be protonate fully because this was not as acidic as one of these. Now on the page we're about to go to, which we've already covered, it was an indirect route. What we did essentially was, on the very next page, we added an ester here. Was it an ethyl or methyl? We added an ester there on that. And then we did anion, same thing. But then we had to remove the ester. You see, the ester was added just to make that more acidic so you could use a weaker base. So if we turn over, see the ester's been added to make that carbon, those CHs more acidic so we can use a weaker base. We did the reaction, but then we had to take the ester off. How did we take it off? We first hydrolyzed to the acid, but because it was a beta-keto acid, the acid was lost, the CO2 was lost, and we ended up with the same product as on the previous page. So we did it indirectly, and we used a weaker base, which is more convenient. So really, we just used this ester to our advantage. And after we used it, we got rid of it. Okay? The ester was kind of a dummy or activating group. And that's essentially kind of what we're doing over here too. Acidic, we do the chemistry. Now when we hydrolyze, we have to hydrolyze both esters. We get the diacid. But when we lose one, we end up with an acid. So one of your carbonyl groups remains. If you want to convert this back to the acid, how would you do it? Treat this with methanol and H+, and you get back your ester, right? What's that reaction called? Fischer esterification? Yeah. So get your ester back to a Fischer esterification. Question, why did we use sodium methoxide here? Why didn't we use sodium ethoxide? Or sodium hydroxide? Why did we use sodium methoxide as the first step? Will methoxide add to carbonyl? Yeah, it will. If we add to carbonyl, electrons up. And then back down and kick that off, what do we get? We don't get anything new. That's why we use methoxide when we have a methyl ester. Well, if it adds to carbonyl, kicks that off, so what? It's okay. Now ultimately we're going to remove the esters and get that, so you may not be worried about it. But if you're just trying to make this, if you use ethoxide, you're going to end up with a mixture of methyl ester and ethyl esters because of this additional elimination potential. But if you use the same base as here, nothing will happen. You won't make anything new. Okay, so there were some examples of using ester groups as dummy groups, but then you can hydrolyze and remove them. Any questions about that indirect route? decarboxylation. Let's pull out the white set from the we've been looking at along the way. It says aldehyde ketone on the front with a picture of triamcinolone. Let's look at the industrial synthesis of Vioxx. Anybody remember Vioxx? About 10, 15 years ago. Anti-inflammatory, like a COX-2 inhibitor. They were making billions of dollars 15 years ago. Unfortunately, Vioxx turned out to have some heart side effects, and it had to be pulled from the market. They're trying to revive it a little bit. You occasionally see commercials on it. At the end of the commercial, it's got this like 10-second warning. Here's Vioxx. Just like the majority of drugs, 89%, they're fairly small organic molecules. Okay? $1 billion right here, though, for a company. How do they make Vioxx? Everything we've seen except for right here. You can buy this. It's called thioanisole. Do a Frito Crafts. Yeah. Acylation pair. You may also get some ortho. But that can be purified out. Frito Crafts do kind of prefer a pair. We've not seen in this class oxidation of the sulfur, but it can be oxidized to what's called a sulfone. From there they do bromine acetic acid. What are they doing? Alpha bromination. Why does it not brominate the ring? Can you brominate the aromatic ring? Sure. What do you typically need to brominate the aromatic ring, though? Lewis acid. Well, acetic acid is a proton acid. Typically, though, in this class, whenever we brominate or chlorinate rings, we use like FeBr3 or something. It certainly could. It could. But both of these groups are withdrawing groups, deactivating the ring. So apparently it does not, and it just does the alpha bromination, which we covered in this class 2 or 3 days ago. What's the key intermediate when you brominate here under these conditions? What's the reacting species? What attacks bromine? Enol, right? Okay. At this point, well, what's bromine good for? Potential leaving group. They didn't come in with this. It's actually a carboxylic acid anion. And they kicked it off in a good old-fashioned SN2, and they just made this bond right here. Nucleophile displaces the bromine. Then from there, what do? From there, they do an aldol condensation, an aldol reaction, using triethylamine, which is a fairly weak base, but it is strong enough to do an aldol. When they do an aldol, they get the final product. It's actually where an internal, what do you call an internal reaction? Intramolecular. It's an intramolecular aldol. Okay. What small molecule is produced here? I'll go ahead, well, it says condensation. What does that tell you is produced? Water. Yes. You eliminate water. Okay. Let's look at alpha condensation reactions. The main one being aldol. Let's look at this aldol reaction. There's various types of aldols. They're symmetrical and non-symmetrical. Symmetrical, you're going to have two of the same molecules reacting with each other. Some people call that a homoaldol. First example is a symmetrical aldol. You take acetophenone and treat it with just a little bit of hydroxide catalyst. Acetophenone will react with itself, and you'll get this here, plus water. Now this is a mechanism that, if I gave you 10 minutes for the first time, I would hope that most of you could do this. It's not much new. Now there's two of these, so let's go ahead and draw another one up here. Okay, what do you want to do first? Chris?
Deprotonate.
Deprotonate what? One of these H's on the ring?
No, it's on the ring.
Right here?
Yeah.
Yes. We have hydroxide, deprotonate, we get, I'm going to call this phenyl 1, I'll eventually maybe call that phenyl 2 right there. So we're going to make the enolate. You can do the resonance structure, which looks like really the enolate with the ene and the O minus. Okay? Now we know that this is not highly favored because what do we make here? What else are we making here? Water. pK, that's 16, this is 20. So which is favored? Actually 20 is favored. I'm not going to make much of this. But we are going to make one molecule of it at least. What can that one molecule do? This will attack the other carbonyl. Electrons up. What does that give? That's going to be 2 over there. Phenyl 1, see, one of the first things we have to do is we have to keep track of all of our atoms and what's attacking what. This carbon just did what? Made bond to carbonyl, and the oxygen electrons went up. So we just made this bond. That used to be a carbonyl. What was on the carbonyl? A methyl and a phenyl 2. A methyl and a phenyl 2 were on the carbonyl. You see how the alpha carbon just attacked the carbonyl electrons up? I'm going to label this is 1 and that's 2. Okay. What are we trying to accomplish? We're trying to get double bond between the original enolate carbon, alpha carbon. This carbon over there, the alkene, was originally what? It was originally that carbonyl carbon. How did we get there? That only has one oxygen. One of these oxygens has to be eliminated. Which one? Left or right? Right. Because phenyl 1 has carbonyl. What do you want to do next? Sarah? What do you want to do next? We got to eliminate this oxygen. What do you want to do next? Protonate it with what?
With water.
Yes. Protonate it with water. That's the strongest acid we have available. We do not have any acid. We do have water, which can act as an acid. And so we're going to protonate this, and we're going to get that there plus what? Importantly, the plus what's important along the way here? What do we make here? Plus hydroxide. Now we reform hydroxide when we took an H from water. Is this favored? Well, what's the pK of water? 16. What's the pK of the acid over here? Alcohol. What's its pK? 16. You see, this is favored. It's like, I mean, it's 50-50 there. It's 50-50. It's going back and forth. In fact, this is going back and forth. because anytime you can make a pi bond and kick off a leaving group, that's easy to do. So that oxygen can keep that enolate back off. And once it gets kicked off, we know that that's the prepared form here, so all this is equilibrium. So this is called this is the official Aldol product. Right here. Why is it called an Aldol? What does the OL ending mean? Alcohol. You see this alcohol here? Aldol is because there was this is traditionally done more, it's more common to do this with an aldehyde. You can do it with ketones too. Early on, they must have did it with aldehydes. Started with aldehydes and they were getting these alcohols and somebody said Aldol. Okay? That's where the name came from. But Aldol products, that's certainly not that there. And some people would actually call this an Aldol product. This is non-dehydrated. Non-dehydrated. And it's unfortunately just confusing. Somebody says Aldol product, you gotta say, do you want the hydrated one or the dehydrated? OL, alcohol. Okay, how do we get to this? From here to here, what do we have to lose? I lose water. How are we going to do it? We got hydroxide. I told you at the end of the quiz, anytime you can do acid base, that's what you're going to do. Do we have acidic H's here? This could take that H, but you're going backwards. Ah, how about that H? Aren't these acidic? Yes. Hydroxide can take this one, and that gives that anion plus what? Plus water. I'm going to put that in a box because that's actually this water now. There's that water. Now from there, how do we get final product? Anytime you make a pi bond and kick off a leaving group, that's easy to do. And what does that give? That gives that plus what? Plus our catalyst. But hold on. OH is not a good leaving group. Back when we did alcohols, we said we had to protonate them or turn them into tosylates. Why is this a good leaving group? Is this we eliminated this here. Is this an E1 or E2? It's neither. No. It's neither E1 or E2. If it was E2, we would have taken the H, electrons would have moved in and kicked off the leaving group altogether, right? We didn't do that. If it was E1, what's the first step of E1? In general, the first step of an E1 is the leaving group leaving. Now maybe we could, that OH is not going to leave on its own unless you protonate it. We're not under acidic conditions. To eliminate from here, we did neither E1 or E2. It has a different name, I'm not going to name it. But what we really did was, the only reason we could make this anion is why? These H's have some acidity. I mean, if we just had this alcohol here, you would never make carbanion and then eliminate it. Because those aren't acidic. But these are. Remember, we can do chemistry here. That's what we said. These are acidic enough to do chemistry. You make the carbanion, And then boom, we can expel the leaving group because, say it with me, anytime you make a pi bond, kick off the leaving group. Question?
So why would it do E2?
Why would it do E2?
Yeah.
Because OH is not a good leaving group for E2. Hydroxide is not a good leaving group. This is a fast step. This is a fast, non-rate determining step. Hydroxide is a poor leaving group in a rate determining step. And if you look at E1 and E2, the leaving group leaves in the rate determining step in both of those mechanisms. But here it's not. Because anytime you make a pi bond kick off a leaving group, that's a fast step. Mainly predicated because these are acidic and we can make the carbanion. Okay, this is an Aldol reaction. Altogether it's called an Aldol condensation because we lose water. That was symmetrical because two molecules reacted with itself. The product can be cis or trans alkene. Ultimately, what are we making in an Aldol reaction? Ultimately, you're making an alkene. Okay? But you're going to have a carbonyl usually because, okay? Please look ahead. Let me take you through this in 30 seconds. Down below, we're doing mixed aldol. Two different aldehydes and ketones. Please rationalize why you get 4 potential products down here. Where the one we just did only gives 1 product. Why do you get 4 down there? Next, on the back side, we'll do mixed aldols that work okay. Then we'll do intramolecular. You remember the Vioxx? That was an intramolecular. Look at the Vioxx, look at that mechanism, do the mechanism. There, triethylamine is the base instead of hydroxide. And then we got to be able to think backwards. Can you make this by an aldol reaction? All of these, yes. Show the 2 starting materials that would react to give these in an aldol. Well, what components are needed for an aldol? Those are things to think about. We'll do these first thing next time. Then the main topic, one of our main last topics will be Michael addition. Conjugate Michael addition. That'll be our main last topic. Okay guys, see you Wednesday. By the way, okay, here's what I decided. Lab was canceled on Friday. This Friday we will do the Vidig lab that was canceled. Okay? The Wednesday group will turn in a group report okay? When you come to lab, Wednesday group turn in your group report. Friday lab will do the Vidig, but you will not do a group report because it's the end of the semester. Instead, you will turn in your notebook pages. Okay? All right. Wednesday's lab just checks out this week. Wednesday lab does nothing this week. Wednesday lab just checks out. On Friday.
When you want to do that?
Do it for some butt.
I mean, work on it. What do you do? Yeah, I'm pretty open today.
You guys want to get together?
Yeah, I'm trying to get together.
To write up our we'll text each other now. Whatever aldehyde you choose on Friday, you can use the same one.
But yeah, we'll just text later on.
Are you working?